Yeah, check, check, check. Cool. Hi, everyone. My name is Horsefacts. You can find me as horsefacts.eth. I'm also ethcall on Twitter, or you can visit my professional website, terminally.online. I'm a smart contract programmer and EVM enthusiast, and excited to talk about invariant testing wrapped Ether with Foundry today. So this is going to be a hands-on workshop if you want to get your hands on. So here are some setup instructions. We're going to be using Foundry today, a build tool and development framework for Solidity. If you haven't used Foundry or installed Foundry, you can follow the commands here to get that installed. And then there's a GitHub repo that has all the code examples from today's talk and some additional bonus content in there if you'd like to use that. You can also hit that QR code up in the corner to reach the GitHub repo. Inside that repo, you'll find a README that has kind of written content of all the contents in today's talk. And you'll find some tags in there as well that you can check out to follow the code examples along the way. We're not going to use those too far in depth today, but you can sort of use that repo to explore as we go along with the talk. And I'll leave this up here for a minute if folks want to check that out while we talk about the goals and agenda. So the goal for today's talk is really just to get everyone up and running with Foundry invariant testing. This is kind of a broad intro to how to use the tool. And hopefully people by the end of this will feel comfortable writing your first invariant tests in Foundry. It's not necessarily an overview of advanced techniques or detailed invariants today. And we're going to use wrapped Ether, a real-world contract with an important real-world place in the Ethereum ecosystem as a motivating example. And this is a good example because it's kind of a simple contract. It's ERC20 contract with a few extra methods that we can use. But it's a good motivating example for today. And yeah, we'll be able to use that throughout this workshop. So agenda for today, we'll talk a little bit about what invariant tests are and discuss how they differ from unit and fuzz tests. We'll take a quick look at the wrapped Ether contract itself, how it works, and what we might want to test in the contract. We'll look at setting up a Foundry project for invariant testing. We'll walk through hopefully testing 3 invariants, conservation of Ether, solvency of deposits, and solvency of balances. Along the way, we'll look at 2 common invariant testing patterns, one called handlers and one called actors. And then if we have time, we'll look at testing our own tests using mutations. And I think we're going to use all the time we have, so here we go. Cool. So what are invariant tests and how do they work? In general, I think of them as a kind of super fuzzing that are built into Forge. If you've written Foundry or Forge fuzz tests before, the concepts here are pretty similar. If you haven't, we can go over unit tests, fuzz tests, invariant tests in turn here. So here's an example of a unit test. You can see we're testing addition. And in a unit test, we're typically testing local behavior with a specific input and a specific output. So in this example, 5 plus 3 equals 8. So we're usually testing one component. We're choosing specific concrete inputs, and usually focusing on a specific function and specific behavior. If you're a very rigorous tester and test-driven developer, you might pick specific concrete cases in your use tests that sort of drive your code forward, right? Like edge cases, specific values, as you're thinking about which concrete values to test. But as you write unit tests, even though everyone should write a lot of them, hopefully everyone's familiar with them, you're never really going to cover the whole range of inputs and outputs that are possible in the domain of your functions, right? You're sort of picking very specific cases that are interesting and useful to you. I like this acronym in unit testing called ZOMBIES, which stands for 0, 1, many, boundaries, interfaces, errors, S. I use security in Solidity. But as you're thinking about unit tests, often you're picking these specific concrete cases, concrete inputs, concrete expectations. We have this metaphor I hear a lot in testing, right, that your unit tests are a safety net. They'll catch you when you fall. But I think that's kind of a bad metaphor in some ways, right? Unit tests are really like you're climbing a rock wall and you're hammering little pitons into the wall or something. You're picking these very specific points out of the entire domain of your function to test. So a fuzz test, another form of testing in Foundry, is kind of like a parameterized unit test. So in a fuzz test, we're testing the properties of one component, typically local behavior, but now we're testing it with random inputs. And instead of an expected concrete output, we're expecting a specific property in this test. So local behavior, random input, expected property. So in this case, we're still testing addition in this code example, But here we're testing that addition is commutative, right? So a random value for A, pick a random value for B, and we're going to assert that A plus B is equal to B plus A. So yeah, when the fuzzer runs, it's going to generate many random concrete inputs for this test. It's going to verify that the property we've defined here holds for each one of those inputs. And fuzz tests are kind of a broad category. They can be pretty extensible. If you want, they can be narrowly focused like unit tests on a single component, a single behavior. Or you can build them into something that's maybe more broadly focused on multiple components or the system as a whole. But in most cases, I'd say a fuzz test is still focusing on function local behavior rather than trying to test the whole system at once. So finally, an invariant test applies the same idea of testing properties to the system as a whole. So rather than defining the properties of specific functions, we're going to define invariant properties about a specific contract or system of contracts that should always hold in the system. So yeah, here are some examples of invariants you might write for a smart contract system. A vault contract always holds enough tokens to cover all of its withdrawals. X times Y always equals K in a Uniswap pool. That's a really famous invariant. LPs should only ever be able to withdraw the number of staking tokens they deposited. An ERC20 token supply always equals the sum of its individual balances. And so during an invariant test run, the fuzzer will run against all functions in all contracts versus a fuzz test where it's targeting a specific fuzz test with specific input parameters. So the fuzzer now runs against all the functions it finds in all of our contracts. It tries a sequence of random calls with randomly generated call data, and it checks our defined invariants after every call. And if any one of those call sequences breaks the invariant, the tests fail, and it produces a counterexample for us that can show how it failed. So invariant tests are a powerful tool. I think they're probably the most advanced testing feature in Foundry. And they can be really good tools for shaking out invalid assumptions, complex edge cases, and unexpected interactions in your smart contract system. But because they're so unconstrained, it can also be very challenging to channel the fuzzer's sort of unconstrained chaos into a suite of meaningful, reliable, useful tests, and also to avoid kind of making assumptions that might fool yourself along the way, and keep your tests testing what you actually think they are. So we're going to test wrapped ether in this workshop. If you don't know wrapped ether, a quick overview is that it's a contract that allows you to deposit and wrap native ether, which is then represented as WETH, an ERC20 token. And then similarly, if you are holding WETH, the ERC20 token, you can withdraw native ether by exchanging that token one for one for native ether. So wrapped ether is a simple but very critical primitive in the Ethereum application layer for two big reasons. Number one, it enables applications that are composable with ERC20 tokens to use a representation of native ether. So if you've already built a system that is composable with ERC20s, you don't need to add like extra edge cases and semantics for dealing with native ether. And then secondly, it helps mitigate security risks that are associated with transfers of native ether. When you send native ether, you're transferring control flow over to the receiver, which is risky and can lead to reentrancy bugs. So using wrapped ether can help mitigate some of those concerns. Here's the mainnet WETH contract, the canonical WETH contract. There's a link here to WETH 9, which is like the canonical WETH contract on mainnet. This one currently holds, what is this, 3.4 million ether, like $6.6 billion. So finding any bugs in this would be a big deal. And this is just the mainnet contract, right? There are other versions of this contract deployed on other chains as the native wrapped token. The contract is actually simple enough that we can cram it into 4 slides here. It's a little over 50 lines of code, so we can speed run it quickly here. You can see we have ERC20 metadata. We have some standard ERC20 events. We've got a mapping for balances and a nested mapping for allowances. The really interesting stuff are the next 3 functions here, fallback, deposit, and withdraw. So you can see in deposit, if the sender, it's a payable function, right? In deposit, we will credit the sender with the amount of ether that they're providing. Similarly, in withdraw, we'll exchange back and transfer an amount of native ether equal to the WAD amount here that they're withdrawing. And then thirdly, we have this fallback function, which is sort of just a convenience function so that if you send ether directly to the contract, it will wrap it and deposit it for you. Finally, we've got total supply. We've got transfer stuff, approve, transfer from. All the details of this are not super important. The point here is that it's like a pretty simple 50-line contract. Cool. So let's get started writing invariant tests. And just starting by setting up a framework for writing an invariant test in Forge. So fortunately, everything you need to start writing an invariant test is built now into the Forge test contract, the base contract that you import from Forge standard to set up a unit test. So I like to put .invariant in the name of my invariant test files to distinguish them from others, but that's really just a convention. It's not required from the test runner. And a simple invariant test can just look like the example here. Hopefully this looks familiar if you've used Foundry. You can see we're declaring our contract under test as a state variable. We create an instance of that contract in setup, and then we write test functions using assertion helpers like assert EQ here that will make assertions about the state of the system. The one thing that's different here, you might notice, is that the test function is prefixed with invariant underscore. So invariant tests need to start with this invariant underscore prefix. So we're starting with a pretty useless invariant here, but let's just see what happens. This is testing that the total supply of wrapped ether is always going to be 0. And if we run the tests, here's the output that we'll get back. You can see this looks sort of like a standard Forge unit test run, but we have a little bit more information underneath it here. It runs, calls, and reverts. So when you read an invariant run, it's going to print back some sort of diagnostic information about the run. That includes runs. This is the total number of random call sequences that were generated by the fuzzer during this run. The number of calls, so this is the total number of external calls the fuzzer made to our contract during this test run. This is equal to the number of runs times the depth, which is a parameter you can configure in your Forge setup. And that's how many calls will be made in a run sequence. So you can sort of tweak that to have more or fewer calls. And then finally, we have reverts, which is the number of calls that actually reverted in this test run. So in this case, you can see like well over half of our calls reverted. So these were all the randomly generated calls that were made by the fuzzer to our contract. Over half of them reverted. So you might wonder what's going on here. Is this doing anything? This kind of reverted a bunch, but the test passed. So what's going on? One tool we can use here to figure that out is another setting within the Forge config called fail on revert. You can toggle this between false and true to see what's happening in an invariant run. So this will cause those, previously we had this set to false, right? So the test will run, we're sort of allowing the test to fail and revert in the case that anything reverts. If we want to see what has failed, we can toggle this to true, rerun the tests, and look at what's going on. So yeah, switch this to true, rerun our tests, and we can see a failure case here. So this is sort of what a failed test run will look like. And you can see we have some information about the call sequence, the sender, the address that was being called, the call data of those calls, which tells us what calls were made and in what order. So here the call that is reverting is this transfer from, probably because the caller hadn't made an approval, right? So the to address, the from address, hadn't made an approval for this sender address to transfer their ether here. Yeah, so if we look carefully at this fuzzer output, we will sort of discover that what's happening here in this initial test is that basically every call is reverting, except for a handful of calls that are making a 0 deposit or a 0 withdrawal, which is allowed if you look carefully at the wrapped ether contract. It doesn't catch 0 deposits, 0 withdrawals. So this sort of open fuzzing, where we point the fuzzer just at the raw contract, let it kind of wreak havoc on all methods, all arguments, everything it finds at once, can be useful in some scenarios. But this is a good example of how we sort of have to constrain the environment often in invariant testing to actually simulate the conditions that we care about. In this case, we want to actually test making deposits and withdrawals from this contract. The fuzzer by default is not going to do that. So there's an interesting trade-off here, right? There's a trade-off between exploring more random call sequences in invariant testing and finding meaningful sequences that actually test our invariants. If we expose more surface area to the fuzzer, there's much more that we can fuzz, but it means that we use more of these limited runs on things that might simply revert and not test the invariants that we care about. So if everything is reverting because arguments and ordering are not realistic, we might not really be testing the invariants we want to in a useful way at all. And I find this like the trickiest trade-off in fuzz and invariant testing in general, is to think about if you can only do a limited number of runs, how are you going to sort of use those runs as effectively as possible? OK, so in order to sort of constrain our environment and test what we really care about here, we're going to use a pattern called a handler. So a handler is a wrapper contract that we can use to manage interactions with the contract under test. And basically, rather than expose the WETH9 functions directly to the fuzzer, we're going to wrap it in this handler contract. This lets us control the environment. It lets us sort of choose when to expose particular functions to the fuzzer as we build out our test suite. And it lets us use cheat codes like VM prank and deal, things we usually use in Forge, to set up the environment with the conditions that we care about. So a handler is just another contract, as you can see here. Typically, I like to pass in the contract under test as a constructor arg. And then within this handler contract, you'll write wrapper functions for each external function on the contract that you're testing. And then one by one expose those functions to the fuzzer as you build up your suite. So in this example, you can see we're sort of mirroring the interface of the WETH9 contract. Right here, we've just exposed deposit, sort of the first function we want to test. But as we build this out, we're going to expose deposit, withdraw, transfer, transfer from, all of those external functions. And as we fuzz this contract, the fuzzer is now going to generate random calls with random values to the functions we've defined on the handler, rather than the WETH9 contract itself. So an important note here is that it's up to us to pass through those fuzzed arguments to the contract under test, and to think about constraining them, if necessary, within the handler. So here we're passing through the fuzzed amount value in deposit to WETH deposit as the value when we make that call. And second here, since our test contract needs to have some ether balance in order to make a deposit without reverting, we're going to use deal in the constructor here right after we set the WETH contract to deal ourselves some ether in the constructor. So just 10 ether to start. OK, back over in the tests, we need to set up our handler contract alongside the WETH contract. So yeah, this is how this looks. We'll import our handler, set up that handler in the setup function. And then importantly here, we're using the target contract built in. This is part of the Forge test class. And this is telling the fuzzer to now target our handler contract instead of pointing at WETH9 directly. And this is important. Don't forget to set this up. If you don't do this, the fuzzer will find all functions, all contracts that are created during setup, and it'll implicitly fuzz all the methods that it finds on those contracts. So this is a way to kind of target it just to the specific function that we want to expose, specific contract interface that we want to expose. OK, we run these tests now, and we have a successful failure. So unlike our very first failure, which broke right after setup, the fuzzer has failed here, and we have a successful failure, right, what we expect. So the fuzzer has helpfully printed the call sequence that broke our invariant here. Here's the sender, the address. You can see now this is our handler contract, right? We were calling the handler contract rather than WETH9 directly. The call data of the function that broke the invariant. Here it was a deposit. And the arguments to that function. So in this example, we called deposit. We deposited 65 way. And that broke our now invalid invariant that the total supply is always 0. OK, so what should our first invariant condition actually be in this case? I think thinking in invariants can be very different from the way that we think about the system when you're writing unit tests. You need to sort of think about properties of the system as a whole, rather than specific reactions to specific concrete inputs. But here's one invariant we can test. I'm going to call this one conservation of ether. So if you think about our two contracts, we have our handler contract and the wrapped ether contract. Those two contracts are a closed system, right? ETH is only created in the handler when we deal it to ourselves. And it can only flow into WETH9 when we deposit, or out of WETH9 if we withdraw. So we can test this sort of conservation of ether property in this closed system, which is that the WETH total supply plus the handler's ether balance should always equal the circulating supply of ETH in this closed system. So let's update our handler a little bit here. We'll make it like a little bit more realistic. We dealt 10 ether before, but we can use kind of a more realistic value here, right? There's like around 120.5 million ether in circulation. So we'll add this as a public constant on our handler, and we'll deal that amount to ourselves in the handler during setup. And then from here, we can now define our invariant test in the invariant test file. So here's the property that should always hold. The handler ETH supply, which we can access since it's exposed as a public constant, is equal to the handler contract's balance plus the WETH total supply at all times. So for now, we'll also add one more condition to our test, which is to use this bound helper to bound the deposit amount such that it's less than or equal to the remaining ether balance in the handler contract. And this will prevent calls from reverting if we generate a random call that tries to deposit more ETH than is available. We don't necessarily have to do this, right? We could let our tests revert in that case. But for now, as we're building up this suite, I sort of want to focus on testing the conditions that we care about, right? Which is not the revert case. We might want sort of at the end of the suite, once we built out these invariants, to remove some of these bounds and make our fuzz run a little bit more unconstrained, allow more things to revert. But I find that it's helpful kind of as you're building up these tests often to prevent things from reverting and use this bound helper here. If you haven't seen bound before, this constrains a value, right? So we're constraining the amount value here to be between 0 and the balance of our handler contract. So it's not going to try to deposit more than the handler has in its balance. And when you're fuzzing on like a really big uint 256 number, you often generate really big numbers in these runs. Bound is kind of like VM assume too, if you've used VM assume, but it's a better tool because it doesn't throw away the run, right? So you can use bound, it's just going to constrain the value rather than throwing away the run altogether. Cool, run these tests and we should see them pass. And you can see here, reverts is now 0, right? We're never attempting a deposit that exceeds the balance, so none of these calls revert like they were before when we were kind of banging on the contract and over 50% of our calls were reverting. So switching back and forth between open tests and constrained tests and bounded and unbounded calls can be a very useful technique as we write invariant tests. But for now, we're going to kind of keep these values constrained as we build up the handler and invariants. OK, so our tests pass, but we've only exposed one function from the contract under test through the handler. So to test the real-world behavior of wrapped ether, we need to expose withdraw, transfer, transfer from, all the rest of those external functions. And eventually, we'll get to adding transfers and approvals, but let's not add them yet. For now, let's add withdraw and a fallback function. Oh, here we go. Yeah, so you can see here, we've added withdraw. We're also going to use bound, again, to bound the amount that we're fuzzing on here to the balance of the caller. We also need to add a receive callback to the handler here so that when we withdraw that ETH, the test contract can receive it. Send fallback is kind of interesting, right? In this handler function, we need to trigger the fallback function on WETH. So here we're going to, this looks similar to deposit, right? But rather than call deposit directly, we're going to use a low-level call in order to invoke the fallback function and send ETH directly. Cool, and once we've added these, run our tests again, we can see they still pass. So our invariant is still holding as we've exposed more behavior to the fuzzer. OK, let's move on to another invariant. So the second invariant here is solvency. And in order to test this invariant, we're going to introduce a new pattern called ghost variables. So with this invariant, it's important that the WETH contract's native balance is always high enough to cover all possible withdrawals from the contract. All right, otherwise, it would be insolvent. Not everyone could withdraw their ETH. All right, since wrapped ether and ether are convertible one-to-one, the contract's balance should always equal all the deposits that have ever come into the contract minus all the withdrawals that have ever come out of the contract. And in order to test this, we need a way to track all the deposits that have ever come into the contract and all the withdrawals that have ever come out of the contract. So we can use a technique that's called a ghost variable in order to track this. So a ghost variable is a stateful variable we can put in our handler contract, and it's going to track state that's not otherwise exposed by the contract under test. I like to prefix these with ghost underscore. I see folks who use Certora and other invariant testing things like to prefix these with ghost. But really, these are just normal variables, right? It's just a solidity state variable. You can name it whatever we want. So here we've defined two uint 256 variables here, ghost deposit sum and ghost withdraw sum. And we're going to increment both of those, right? When we deposit, we're going to increment ghost deposit sum. When we withdraw, we will increment ghost withdraw sum. And that's going to keep track of total deposits in, total withdrawals out. You might wonder why we don't just decrement ghost deposit sum, right? Just use one variable and increment sometimes, decrement sometimes. I think there are two good reasons. So one is that it's nice to have these sort of intermediate accounting variables available as separate properties. So you may want to define another invariant later that uses these as kind of intermediate parameters. And the other thing is that it's just good to be as wary as you can about adding any complex or conditional behavior in the handler. If you can keep your ghost variables really simple, just keep them as like simple accumulators, you probably should, because the more complex your handler gets, the more likely you are to introduce an invalid assumption that, that breaks your tests in a way that you don't expect. So keep them as simple as you can is kind of a good practice. Cool, so here's our invariant. Since we've set up these ghost variables as public state variables, we can now access them in the test to define our invariant property. So here, the WETH contracts balance should always be equal to the handler ghost deposit sum minus the handler ghost withdraw sum. OK, let's give this a run, see what happens. And here we go. With those two changes we've made, we actually get a failure. So reading failed call sequences in invariant testing is kind of part of the art of learning invariant testing. You'll really learn to like read and debug and decode your call data if you're reading these counterexamples that it spits back at you, especially if you have like a complex nested struct in the interface of your functions. But one thing that's really helpful here is that it's always the final call that caused the invariant to fail, right? So we're getting the whole call sequence here. We can see 3 calls, deposit, deposit, send, fallback. And it's always the third of those after which our invariant failed and we failed the test. So yeah, here's the call data and the arguments that broke our invariant. And you can see it was calling send fallback with the value 1007. Does anyone see what happened here? Yeah. Cool. Yeah, so we forgot to account for deposits in the fallback function, right? There's this other way that we can deposit into WETH that will increase the balance. And we forgot to do our internal accounting in the handler here. So yeah, this is a good example, right, of a way that you can, if you're not careful in your handler about the things that you're tracking and testing, you can maybe not test what you think you are. So yeah, here let's increment ghost deposit sum just like we do in deposit in our send fallback function here. And cool, once we've done that, all our tests pass again. Yeah. Yep. Yeah. It failed just one time, and what it's showing us are the 3 calls in the sequence. So there was a deposit that succeeded, right? We deposited.
It ran like 1,000 times, and among those 1,000 runs, it was just a single failure, or just one was reported here?
Yes, a single failure was reported here. I may have copy-pasted this from a code example, so.
OK.
Yeah, but in this case, yeah, this is the first, I think it's reporting the first counterexample that it found here. So,
OK, because probably, I mean, if it's fuzzing, it would fail like, I don't know, 1/3 of the time, so it's like a huge number of failures.
Right, yeah, it's just going to report one counterexample that it finds. I actually don't know if it holds on to the other failed counterexamples if it finds them.
Okay, awesome, thanks.
Some fuzzing tools will do like shrinking, which is really helpful, where it'll shrink down the failed example to the smallest input it can find. But as far as I know, Foundry doesn't do that. Cool, so that's our second invariant, solvency of deposits. Let's look at another solvency invariant. This is going to be the most complex one, which I'll call solvency of balances. So solvency of deposits was looking at like all the deposits that have ever come in, all the deposits that have ever gone out of the contract. Solvency of balances is a little bit different. For this one, we want to check that the ether balance of the contract should be equal to the sum of all individual balances in the contract, and that includes balances before and after transfers. Right, so we have this mapping of each account address and its balance of the token. We want to look at every entry in that mapping, sum up all those balances, and that should always be equal to the total supply of the token. And this is an interesting one, right? Because even if users transfer their tokens around, this sum of balances should stay the same and remain equal to the contract's ether balance, at least modulo deposits and withdrawals. OK, so this is kind of complex to track, right? How do we want to track individual balances within this mapping, within the contract? One thing we could do is like add a more complicated ghost variable to our handler. We could add a mapping of address to uint 256, track each caller's balance as it comes into the contract. But if you start going down that path, you'll realize pretty quickly that you're just replicating the behavior of the ERC20 token in your handler. And that's something we want to avoid, right? We should keep our handler as simple as possible. So in general, I think it's a good practice to rely on external state from the contract you're testing whenever you can. So if you find yourself adding lots of complex logic, step back, think about whether you can access that information in another way. And to do that, we can, right? So rather than store balances internally, what we can do is save the address of every caller, iterate over each of those addresses and get its balance, and then add up the balances in our test. So here's how we can do that. To do this, we're going to need to introduce a new pattern called actors. And we're also just going to need to introduce this concept of multiple callers, which we haven't yet, right? So far, every call to the wrapped ether contract is originating from our handler contract. So this is not very realistic. Only a single address is ever calling the contract under test. What we want to do is simulate many calls coming from many different addresses. So Foundry does fuzz different message sender addresses on each call to our handler. But since we have this handler contract sitting between the fuzzer and our contract under test, we need to propagate those. We need to pass them along using VM prank in order to pass them through to the contract under test. A second thing we have to think about here is that all those calls will revert if the caller doesn't have enough ETH to make a deposit or enough balance to make a withdrawal. And since our tests are a closed system, right, we've created all the ETH in the world in our test environment when we set it up. We want to actually send real ether or like real fake ether here in this test rather than using a cheat code like VMDeal, which would kind of mess with our circulating ETH invariant, right? So it's important within the handler that we're actually sending using real ETH transfers. So we have a pay helper down here at the bottom, which will help us make those transfers before tests that we need them. Okay, and here's what it looks like in deposit to actually fuzz on multiple message senders. We're going to use VM prank right before we call deposit, pass through the message sender, which will be fuzzed by Foundry in this test. Yeah, and then prior to that, you can see on the line right above, we're going to pay that message sender, pay that caller the amount that they need in order to make this deposit. We'll update withdraw. So you can see here we're going to change the constraint here from the balance of the handler contract to the balance of the caller, message sender. We'll prank message sender, make the withdrawal. And then one additional thing we're doing here is we need to send that ETH back using pay to the handler to keep it circulating the way we expect. And then similarly, we can update send fallback. This is basically like deposit. Pay the caller, prank the caller, pass that through. Cool. So the tests still pass here. We've introduced this concept of fuzzing on multiple actors. Basically, with every call, Foundry is generating a new random caller, and we're passing that through to the contract under test. So we're now testing multiple actors interacting with the contract. What we haven't done yet is like track their addresses, right? We don't know what all those addresses are, so we still need to build up the ability to track those addresses. Okay, so here's one simple way we can do this, right? We want to capture a deduplicated list of all the callers that we care about. We can do so with like a simple append-only set struct here. One way I like to do this is with a modifier and a little struct we can use to hold on to these callers. So here's an address set struct. This is going to store a dynamic array of addresses and then a Boolean mapping that just checks whether we've added a value to the address or not. We're just going to build this ourselves. You could use like opens up an enumerable set or something here if you don't want to roll it yourself. We'll write a few library functions here to add some behavior to this data structure. So here add will just push an address into that array if it hasn't already been seen. Count will just give us back the total number of addresses in that structure. And then while we're at it, let's add this function. So this rand function will grab a random actor address out of that set based on an input seed. So just doing a little modulo here and grabbing a random address out of that set. So we'll use this in a little bit, but not just yet. But I'll show it now so we don't have to go back. OK, let's use this set and the library in our handler. So we'll create this set struct as a state variable. We'll use this solidity using syntax to attach the behavior from the library. And then we're going to add a view function to our handler here, which exposes all the known actor addresses. And I like to pull this all together into a couple modifiers. This is a pretty common pattern in Foundry invariant testing you'll see is this notion of using a current actor state variable that represents the sort of currently selected actor. So what we're doing here is we're going to also add a state variable to the handler called current actor. And this is sort of going to replace message sender in our tests. We'll add this modifier create actor. What this does is set the current actor to whatever the fuzzed message sender value is, and then add it to the set. That add will be a no-op if it's already in the set, right? So it's just going to be added to our actor set. And then this useActor modifier, which takes a seed as an argument, so we can fuzz on a seed and grab a random actor out of that known list of actor addresses. OK, I know that's quite a lot of refactor here, but we now have what we need to write our invariant, right? So here we go. The WETH contract's ether balance should always be at least as much as the sum of individual balances. So yeah, here we can now create an integer here to tally up the sum of all balances. We can grab those actor addresses from our handler, iterate over each of those actor addresses, ask the WETH contract for their balance, and add it to that sum. And then at the end here, we can make our assertion, right? The balance should always equal that total amount that we've tallied up by asking the contract for each actor's balance. OK, final step before we can run this is to update all of our functions in the handler to use actors. So we'll add that modifier here, create actor to deposit. And you can see we basically replaced the places we were using message sender before with current actor. So it's just kind of a helper that sets message sender to this current actor value. Same thing on send fallback. This looks pretty similar to deposit. It's just doing the low-level call. And then withdraw is a bit more complicated. So for this one, we're going to use that useActor modifier, which selects a randomly known actor from the set. And we're going to add an extra argument to the handler function. So this is a seed that we can use, pass through to that modifier, which will select a random actor. So here we kind of want to choose a known actor to ensure that we're testing realistic withdrawals. We could easily just fuzz on a random address here, just like use message sender rather than a known actor from our set. But if we do so, nearly all withdrawals are going to have 0 amounts, because most of those randomly fuzzed addresses don't have any balance in the contract. So what we actually want to test here in our sort of constrained invariant tests is testing actors that actually have a balance in the contract. Yeah, we won't have time to go into detail today on this, but there's a good example in the repo about this handler function in particular, and how it's sort of easy to fool yourself here if you're not careful about checking that the address that you're fuzzing on actually has a balance in the contract. So one technique that's really useful for this, where we don't have time to talk about it today, but is a call summary. So collecting and printing some diagnostic information about which calls are actually being invoked and with what arguments as you're fuzzing. And looking at that to make sure it's like well distributed across the functions you expect. It's not reverting when you don't expect it to revert, stuff like that. Hopefully we have some like better tooling coming in Foundry on that soon that'll help us like collect metrics and data over these runs. But for now, you can roll it yourself. Whew, OK, so there we go. We run this, and all three, after this large refactor, right, all three of our invariants are holding. Cool. So a few more changes we need to make here to expose all the functionality of the contract. So far, we've only exposed deposit, withdraw, and the fallback function. But we need to add the rest of the wrapped ether functions to the handler. And we have our invariants defined now. And at each step here, as we expose these, we expect those invariants to continue to hold. So as we add this functionality, we'll sort of keep running the tests and make sure that they still pass. So here's approve. When we're doing an approval, we'll choose a random spender and just approve them for some randomly fuzzed amount. For transfer, we will choose a random destination address. Yeah, you can see we're sort of hitting the actors set there directly, calling rand directly on it to select that to address. Transfer from is a little bit more complicated. Here we're going to select a random caller, select a random to address, select a random from address for the transfer from. If we were to stop there, again, many of these transfers would revert because it would be unlikely that the fuzzed address, the fuzzed caller, was approved to transfer from, right? So, and a good way to tell that, right, is just run your tests, build this out, run the tests, look at how many reverts there are, right? You may see like, oh, there are thousands and thousands of reverts because most of these calls are failing. So one thing we'll do here is add this Boolean flag for approve. We'll fuzz on that, and then 50% of the time, if that is set to true, we'll explicitly approve the caller before we make that call. So that prevents this from reverting all the time. It will revert some of the time, and that's OK. Cool. And these should still pass. OK, so let's see. I'm just going to try to show some live code. We'll see. So we've made quite a lot of changes to our contracts, to our handler over the course of this so far, right? One thing we'd like to get out of this is sort of a sense of if our tests are still testing what we think they are, right? The quality of our invariant tests themselves. Yes? Yeah. Yes, it's a good question. Yeah, I think this output example may be a copy paste. Yeah. Yeah, that's a good number though to watch like over the course of it as you run these tests, right? Like if you expect 0, you should always toggle that setting back to true and see what it was that reverted to check that. I do find with like native ETH transfers, often you'll get a handful of reverts if you're not careful about constraining it to avoid like precompiles and some other weird, unusual addresses depending on the setup. So that's probably where some of those reverts are coming from. In general, yeah, it's a good practice as you go. Like if you're in the mode where you want no reverts at all, always check those out. Make sure you understand why it's reverting, if it's reverting. And occasionally, if you're in sort of fuzzing in a mode where you don't care if you're reverting, right? You don't mind. Every once in a while, flip that on and check what is reverting to make sure it's not something that's unexpected. Cool, so it'd be nice for us to have a way to test our tests, right? We've built out this handler, it's quite complex. Is it actually testing what we think it is? Is it actually catching bugs in our contract? And this can be tricky, right? Like unlike unit tests, where it's kind of easy to think about, mapping one specific input to one specific output is usually pretty clear. Invariant tests can sometimes be tricky, and they'll accidentally pass if you've introduced an incorrect assumption about your system. So one way to ensure our tests are actually working is to test our tests by introducing artificial bugs. One thing we can do here is like intentionally break some of the production code, run our tests, and then see if they fail. So here's a little diff, a little patch we can add. Rather than actually crediting the caller with the message value amount that they're providing in deposit, we'll just credit them with one way, right? Ignore their amount and credit them with one way. And so a technique I like to use here sometimes is to save some bugs in the contract under test as git patch files in the repo. And then you can sort of reapply them from time to time, double check that the test suite still works as expected. This is kind of a quick and dirty mutation testing framework. So yeah, here are a few other bugs we might introduce. We'll change withdraw to just send back one way instead of the full amount. Here's one where we'll remove the call to deposit from the fallback, so it's not actually invoking that anymore. And then we can add, here's a simple little make file that we can use to apply a patch out of that directory, run the tests, and then check that they fail. So if we sort of git apply each patch in turn, verify that the tests catch that bug. In this case, we want to see them fail, right, rather than see them pass. We can be confident that our tests are catching those bugs and our tests are working. So this is just a quick and dirty form of what's called mutation testing. Hopefully this is coming to Foundry pretty soon. There's an open thread on adding support for Gambit, which is a new tool that Sertora is working on for mutation testing. Maybe we can actually show one of these. Yeah. Yeah, so here's an example. We applied that bug1 patch, ran the tests, and we can see it broke one of our invariants here. So yeah, this is a good sign that our test suite is actually testing what we think it is. OK, so our tests may seem to be pretty comprehensive, but we have kind of one final boss before we can call them complete. And this is an interesting one. There's actually one intuitive invariant you might think should exist in the WETH contract that famously doesn't hold. And it has to do with the way that it's calculating total supply. There's a great post from Stephen at Zellick who used Z3 to do some formal verification on WETH and talks about finding a violation of this invariant. So here's how the WETH contract calculates total supply. I don't know if folks see an issue with this. There's a hint in the title of the slide. Yeah, so rather than storing the total token balance in a separate state variable, it's using this sort of shortcut by just using its total ether balance as the total token supply. And this saves gas over time, but it actually breaks this invariant that total supply equals the sum of all balances. And that's because there's one way that we can force the contract to increase that total supply value without actually creating new wrapped ether tokens. And that's by force sending ether by calling self-destruct, which will force push ether into its contract balance. So the Foundry fuzzer tests a lot of things out of the box, but it's not going to like force push ether to particular addresses unless we configure it to do so. So we're going to need to simulate this scenario in our handler ourselves, and we can do it with this simple little contract here. So this force push contract just has a constructor, takes a destination address, and immediately self-destructs itself and sends whatever ether was provided when it was created. So we'll also expose this force push function on the handler, which will invoke that contract and force push some fuzzed amount to the wrapped ether contract. OK, so once we've added this to our handler, we run the tests. And fortunately, we can see two invariants have failed here. The solvency balances invariant and the solvency deposits invariant both failed. So one thing we could do here is like relax our invariant definition, right? Maybe the invariant here is just that the contract balance is at least as much as all the deposits. It could be more. But we actually have the ability to account exactly for the amount of force pushed ether, right? We can make it a little bit more rigorous than that. So let's do that. Same pattern as before, right? We can account for the amount of ether that's been force pushed into the contract. We'll use a ghost variable to do that. We'll increment that on force push. And then we can update our solvency invariants here to account for that. Right, so now in solvency of deposits, the contract's balance should always be equal to the total amount of deposits that have been made plus the total amount of force pushed ether minus the total amount of withdrawals. And then similarly here in balance solvency, we'll subtract out the force pushed amount from the total. Or we could add it to the other term there, I suppose. And sorry, this is an outdated example. It's using this like reducer thing, which we didn't have time to look at today. Cool. So we'll give those like a final good long run here, 25,000 runs, a pretty deep call depth here, and we can see that all our invariants have passed. So those three invariant tests are all passing. So I think invariant tests are a super powerful tool in Foundry. But this case of like force pushes especially is an interesting illustration of one of their blind spots, right? If we were using like a symbolic test or maybe a more fully featured fuzzler that's modeling those ether sends via self-destruct, it would probably catch that bug pretty quickly. But in fact, we nearly missed it with the fuzzer. We had to rely on our own knowledge about the WETH contract to cover it. On the other hand, invariant tests are much faster to run. They're pretty good, right? Fuzzing gets you a lot of the value that you would get out of many more sophisticated methods. And they allow us to build up a suite of reasonably high confidence invariant properties that maybe we want to invest more in testing over time, right? We might want to further verify those invariants that we've defined using even more powerful tools. And I find them especially useful as you're developing your system, right? As you're working along the way, as you're thinking about invariants, going back and forth and kind of defining these yourselves causes you to think about the actual invariants in the underlying code under test. But yeah, it's important here to remember that all types of fuzz tests, invariant tests included, are probabilistic, right? So unlike a symbolic test that's going to explore all possible execution paths, fuzz tests are only as good as the random data that they're generating. This is still really, really good most of the time, but as with all smart contract testing, we should really do it all when we can, right? Write unit tests, write fuzz tests, write fork tests, write invariant tests, and use formal verification when we can. OK, that's it. Thank you, everyone. Please, if you want more details, check out the repo. There's some additional content in there. And you can follow me on Twitter at @ethcall.
Is there any question?
Can you share any hands-on experience on how to run fuzzy tests for continuous integration? And so the last run I saw was slightly less than 2 hours.
Yeah.
I suppose this is not something you would do on every push, or I don't know, can you parallelize this? I don't know,
Yeah.
GitHub Actions, I don't know, build kite, I don't know.
Yeah, so Foundry will let you configure profiles in your foundry.toml. That's pretty useful to set different parameters, right, for the depth of the run that you want and the length of the run. Yeah, and I think sort of depends on the stage of production that you're targeting with your CI run, right? You want to run them frequently as a developer and maybe often when you're checking into main, and then do some very intensive fuzzing before you deploy to production. Yeah, I think a good example you might want to look at is the Seaport repo has some good configuration for different fuzz runs and fuzz configurations for different environments.
Someone want to add something?
So the self-destruct thing is a little scary there because you think you have this beautiful invariant, you think you've got it, and there's something you actually have to work to test. Is there anything besides having a list of gotchas that you kind of go through to work around that or catch things like that?
Yeah, that's a good question. I think one technique that really helps is building this suite up alongside the development of your contracts, right? Which causes you, it's kind of like test-driven development, right? It causes you to stop, think about the assumptions at each point, think about how things could go wrong. But yeah, like it's an important underline here that there's no magic bullet for testing, right? There's no tool that we can just point at our contracts and find all the errors. There's some really good tools out there, but they all rely on your knowledge of the contract itself, your expectations about the contract itself, and your knowledge of potential errors and gotchas. Yeah. So I think the more we can model those gotchas in the tools that we use, the better. There are a lot of tools that do that. But yeah, it's a tricky problem. I don't have a good answer.
Thank you.
Thanks.